Hello students, in today's class we will see briefly about properties of continuous time Fourier series. Basically why we study the properties because in some cases they can be useful to simplify the analysis of more complex signals. That means if we know, for example, the Fourier series representation of some signals, we can use them to find the Fourier series representation of more complex signals, some other signals. And also, the properties are useful, for example, to find some parameters, like, for example, the power, the energy of signals. For example, instead of doing it in time domain, we can use the frequency domain. So let's see some of the properties. When we study the properties, the first step is knowing the Fourier series representation of x of t is ak. So we start from this. This is our baseline, so our starting point. If the Fourier series representation of x of t is ak, then the Fourier series representation of y of t is bk. One property is linearity. Then if I have alpha times x of t plus beta times y of t, so I have another signal which is a combination of x of t and y of t. Then the Fourier series representation of this combined signal is alpha times ak plus beta times bk, linearity property. The other property is conjugate property. The conjugate property, if I have the Fourier series representation of x of t is ak, then if I conjugate the signal, then I have x conjugate of t. Then the Fourier series will be the conjugate of ak, and also there is a flip, time reversal, a minus k. Okay? So it will be conjugate and time reversal a minus k. If I have a real signal x of t, then the conjugate of x of t is the same as x of t. Okay, so that means a minus k will be the same as ak conjugate. Okay, a minus k will be the same as, first ak will be the same as a minus k conjugate. Then if you simplify, a minus k will be is the same as ak conjugate. So this property is called conjugate symmetry. Conjugate symmetry. So the time reversal of AKs will give me the conjugate of AK. That means. By the way, all properties have the proof in the book, and you can follow from the textbook. And the other property, time shift property. If I have x of t, then time shift by t naught, I have xt minus t naught. What happened to the AKs? The AKs will be phase shifted. No change in the magnitude of the AKs. The absolute value stays the same, but there will be phase shift. So the result will be AK times e raised to jk omega naught times t naught. Okay, omega naught times t naught. We can use, for example, time shift property to find the Fourier series representation of this periodic impulse train. Remember, we studied it, but it's shifted by t over 2. So before it was at 0 first, so now it will be at t over 2. The next one will be t over 2 plus t, 3t over 2, and so on. So this is a shifted periodic signal. So when I shift it by t over 2, in the previous class, we found the AKs. Remember the AKs for that signal. If I go back, this is the periodic impulse train. The AKs are 1 over t for all k. So now what about for the time shifted one? For the time shift, I will have e raised to jk omega naught t over 2 for the time shift factor times ak. So e raised to minus jk omega naught times t over 2. What is omega naught? 2 pi over t. So 2 pi over t times t over 2 e raised to minus jk pi. What is e raised to minus jk pi? This means e raised to j pi, the power of k. E raised to j pi means negative 1. Negative 1 power of k times ak. But ak is 1 over t, so it will be negative 1 power of k times 1 over t, which is, it will become negative 1 over k over capital T. See, so by just using the properties, we do not have to calculate again the AKs, because we know this is a time shift, so we use the time shift property to get the AKs. Another property, time reversal of a signal x of t. If I have a time reversal signal, this will be x of minus t. The Fourier series representation is this. And if the Fourier series representation of x of t is ak, then the Fourier series representation of x of minus t will be a minus k. So the time reversal of the continuous time signal will result in a time reversal of the Fourier series coefficients. That means if x of t is real and even, real signal and even, okay, remember even signal, for even signal x of t is equal to x of minus t. This, therefore, the ak will be is equal to a minus k. That means for a real signal. And for real and odd signal, x of a minus k will be minus of ak. Okay, these are some of the properties. Another very important property is Parseval's relation. Parseval's relation says you can compute the power in time domain using this formula. This is the average power of the periodic signal over one period. So the integration of absolute value of x of t squared dt over one period divided by the period will give me the average power of the signal over one period. You can get it in time domain using this relation, and you can get it in frequency domain using this relation. Using this relation means summation of the AKs from k minus infinity to infinity, absolute value of AK squared. This is very important relation because some signals, for some of the signals, it's difficult to compute this integration. Okay, when you have when it is not easy to compute this integration, you can go to frequency domain and you can use this summation, especially if this summation is convergent. Means if the summation of this series is convergent, it's very easy to find the power using frequency domain. If I have, for example, a few number of case, or if the A case are approximately 0 for higher number of for higher k, then you can use this approximation. The other property is multiplication property. If you have two periodic signals, one, the Fourier series is AK, the other, the Fourier series is BK for y of t. Then if you multiply x of t with y of t, what happened? Multiplication in time domain, and the Fourier series representation of the product signal CK, if I call it CK, will be convolution of AK with BK. See, remember convolution. Now we do the convolution, and our axis will be k now. So a discrete time convolution, that means AK convolved with BK. Okay, of course you will get a periodic signal also in discrete time. So the multiplication in time domain will be convolution in frequency domain. Okay, for the Parser-Bals relation, we can have example here. For example, let's say I have a signal x of t, a naught times sine omega naught t. Prove both sides of the Parser-Bals relation. That means both sides means make sure that the power computed from this relation is the same as the power computed from this relation. Okay, so first we calculate the power in time domain, and then we calculate the power in frequency domain, and we show that both are equal. Okay, so let's see this example. So the signal is x of t, a naught times sine omega naught t, where a naught is amplitude. As you see, this is a sine signal with amplitude a naught. So let's do the first part. So first part is calculate the integration over t of absolute value of x of t squared dt over one period. Select one period from 0 to capital T. So we select one period from 0 to capital T. A naught sine omega naught, square it, a naught square sine square omega naught t. Sine square theta is 1 minus cos to theta over 2. So I put here for sine square omega naught t 1 minus cosine 2 omega naught t divided by 2 integration dt. Okay, so I have two parts. First part 1 over t, the integration from 0 to t, n a naught square over 2 dt. The other part 1 over t is common, a naught square over t from 0 to t cosine 2 omega naught t over 2 dt. The integration of the first part is integration of dt is t, then evaluate from t to 0 is t, so t will cancel t, and I have a naught square over 2. The integration of the second part is a naught square over 2t. The integration of cosine is sine 2 omega naught t over 2 omega naught. This evaluate from t to 0, so it will be a naught square sine 2 omega naught t. But what is sine to omega naught t? Substitute omega naught 2 pi over t. It will be sine 4 pi, which is equal to 0. So the result is a naught square over 2. So the energy, the power of this signal, periodic signal, is a naught square over 2. Actually, we saw this in chapter 1 also. And the RMS value is square root of this, which is a naught over square root of 2. Now we found the power in time domain. Let's find in frequency domain. So find the X. We use Euler identity. So A naught sine omega naught t is A naught over 2j e raised to j omega naught t minus A naught over 2j e raised to minus j omega naught t. The X are A naught over 2j plus or minus. For k plus of minus 1 and 0 otherwise. That means A1 is a naught over 2j and a2 minus a over 2j. Then we do not have other case. A case will be 0 for the rest. So we use a formula, the summation of this absolute value of ak square from k minus infinity to infinity, then from k minus 1 to 1. So we just take a1 square, absolute value of a1 square plus absolute value of a minus 1 square. So absolute value of a naught over 2j. We remove j now, and it will be a naught square over 4 plus a naught square over 4, which is equal to a naught square over 2, which is the same as we computed in time domain. So therefore, the time domain computation is equal to the frequency domain computation. The power calculator in time domain is equal to the power calculating frequency domain. So this example is for simple AC signal. You can try for other types of signals, for example, for rectangular pulse signals or other type of periodic signals. Okay, another example is let's find the Fourier series of this signal g of t. If you see this signal, this is a square wave. It is equal to half between 0 and 2 and negative half between 2 and 4, and then it will repeat. Okay, this is g of t. This is the function g of t. Now I can use linearity property and time shift property to find the Fourier series representation of this g of t. Okay, first g of t can be constructed from these two signals, one constant and the other x of t minus 1, where x of t is the square pulse signal this, where t1 is 1. So it's a periodic signal. T1 is 1 means between negative 1 and 1 it is 1. Okay, so this is the period. The period T is 4. Okay, the period T is 4. It's periodic with period 4. So between negative 1 and 1 is 1. After that, between 1 and 3 is 0. And so on. This point is 3, this point is 5. Between 3 and 5 is 1, and so on. So this is x of t. And if you draw x of t minus 1, shift this square pulse by 1, and you will get between 0 and 2, 1, and between 2 and 4, 0. Okay, so you have a periodic signal. Between 0 and 2 is 1, between 2 and 4 is 0, and then it will repeat itself. So g of t is x of t minus 1 minus half, a constant number. Now, what is the Fourier series representation of x of t? For this signal, we already found it for a square pulse, general form of like this. AK is 2t 1 over t. From the previous lecture, we found it. For k is equal to 0, and sine k omega naught t1 over k pi for k different from 0. Now we just substitute what is t1. T1 is 1, capital T is 4. So we get AK is equal to half for k is equal to 0, and sine k pi over 2 over k pi for k different from 0. Okay, this is for x of t, where x of t is like this: 1 between negative 1 and 1, 0 here, and again 1 between 3 and 5, and so on, right? But we need the shifted one, x of t minus 1. So shift it by 1. So we use the time shift property. So x of t minus 1, for g of t, x of t minus 1 minus half, it will have x of t minus, for x of t minus 1, let's call it bk, and for minus half, let's call it ck. So what will be bk? It will be e to the power of jk omega naught jk omega naught times t naught. The time shift t naught is 1 times ak plus ck. Ck is for the constant part. Okay, so bk e raised to jk omega naught t naught times ak, t naught is 1. So omega naught is 2 pi over capital T, which is pi over 2. So it will be e raised to minus jk pi over 2 times ak. So bk will be at k equal to 0, this will be e power of 0 times a0. A0 is half, so bk is equal to half for k equal to 0, and e raised to jk pi over 2 sine pi k over 2 over pi k for k different from 0. So we found bk. Then what is the Fourier series of ck? Ck is the constant part, negative half. The Fourier series of ck is just a DC constant part is equal to minus half for k is equal to 0, 0 for k different from 0. So if you have any constant number, the Fourier series representation of is itself because it's DC, it's constant. So ck is minus half. Then you add bk plus ck. So you add this one, this part, okay, for bk and this. So for k is equal to 0, you add half. K is equal to 0 minus half, half plus minus half, 0. For k different from 0, ck is 0. 0 plus this part will be this part itself. Okay, so using linearity property now, we found finally dk, which is bk plus ck, is equal to 0. For k is equal to 0, and it is sine k pi k over 2 over k, pi k times e raised to minus jk pi over 2 for k different from 0. So that means we found the Fourier series representation of this periodic signal. Okay, what you will do, try to find it directly by applying the formula, and directly that means you find ak is equal to 1 over t integration of g of t times e raised to minus jk omega naught t dt, and take one period from 0 to 4. Okay, do the integration and prove that the result is the same as this. Okay, which we found this using linearity property and time shift property. The two are the same. So basically what we did, we found the Fourier series representation, another signal using linearity and time shift property, which is an example an example of the application of properties. Okay, so the properties are used to find the Fourier series representation of more complex signals, and they are also useful to find some parameters. For example, we showed how we can get the power and the energy of a signal and so on. Okay, so try to see some other properties from the textbook. And with this, we finish this lecture. Thank you for listening to this lecture.